Now let's look at this example. We still consider z equals 5x plus 4y. And the shaded region is the region which is called the feasible region. Okay, and this feasible region is unbounded. Which is called unbounded region. So you can see that, and for this z, okay, for this z, so if you solve it for y, you will have y equals negative 5 over 4x plus z over 4, right? And z is decreasing, then this line will go this way, okay? The line will move horizontally, parallelly down, right? In other words, if z is increasing, the line will move parallelly upward, right? So it will move up if z is increasing. Right? It's the same as it will move down if z is decreasing. So for this one, if you move the line, okay, if we use the blue color, okay, if this represent our line, it will move up, right? It will move up here, right? It will move up. So because this boundary this region is unbounded, so it will move, the z could be, all the values x and y in this region will make this z as large as possible, right? Because for our line can move up parallelly forever, right? Because these are all the regions of z. So this problem has no maximum values, right? But we have the minimum value. One of these 3 points, corner points, will give you the minimum value, but we just don't know which one is, right? So for the unbounded region, we cannot determine the maximum value or the minimum value exists or not. It depends on the function z. Okay, what is that? If you have this function, z function, a function z, then it will tell you it would be a maximum values or the minimum values, right? But for this problem, for this specific problem, z equals 5x plus 4y, then the slope is negative, so it will go, the line will in this direction, right? The line will in this direction, will be this direction, so it will move up as z increase. And since it's unbounded here, so then this function z can move up forever for this shaded region. So z has no maximum values, but it should have a minimum values because it will touch this region. At the first point, it will touch this region would be the minimum value, right? It will give you the minimum value. But which one is the point gives you the minimum value of this z? Okay, the smallest number of z. So we need to test. So we just draw a table, right? We draw a table, list the corner point. The one is 0, 9. And the one is 3, 5, 2, 3. The other one is 5, 0. Okay, what is the z values? So we plug in z equals 5x plus 4y. So this z equals 5x, 5 times z plus 4y, 4 times 9, which is 36. And this one is z equals 5 times 2 plus 4 times 3, which is 22. And this z equals 5 times 5 plus 4 times 0, which is 25. So in other words, this is the point it will touch. The line will go upward, right? And this is the first point it will touch this region. And it will give you the smallest z values. The smallest z values, the minimum of z is equal to 22. And the maximum of z for this unbounded region does not exist. Okay. So actually, for the unbounded region, it depends on the specific form for the z functions. It will tell you the maximum value or the minimum value exists or not. So now let's look at the linear programming. So for the linear programming problem, the linear programming problem consists of two parts. The first part, which is called the objective function. The objective function is the aim of this problem, okay? So we want to, for example, we always want to maximize or minimize the objective function. So like, for example, we want to maximize the profit, okay? So this is the kind of the aim, the question of this problem, of the linear programming problem. So what is our aim? So we want to maximize or minimize some objective function. So the objective function is always written as z equals a function of x and y. So here, xy is called the decision variable. So here, I write here, x, y are the decision variables we need to introduce by yourself. Okay? So this is the first part. We want to maximize or minimize the objective function z, which is a function of x or y, and x, y are the decision variables you will introduce by yourself. And the next part, which is called the constraint. Okay. The constraints are formed by some inequalities. Okay. So these are the actually form a system of inequalities. So last time, the previous section, we have learned how to find the region for the solution region for the system of linear inequalities. So here, and this region is called the feasible region. It will give you which is called the feasible region. Like we did in the previous several examples. So this is the feasible region, which is formed by the boundary, which is a line. Line is a linear functions, right? So which is actually what we learned last time, how to find the region, the solution region for the system of linear inequalities. So this would be the feasible region. So these are the two parts of a linear programming problem. Okay, this is the one part. This one is the other part. Okay, every problem always consists of these two parts. Then we know if we have a system of linear inequalities, then we can always draw the graph to find the feasible region, right? To find the feasible region, then we have some objective functions, right? We want to maximize z on this feasible region. That means x, y should lie in this feasible region, right? Then the previous several example gives you an idea how to use the graph, right? The geometric approach to get the maximum value or the minimum value of z. We just needed to test the corner, okay? We just needed to test the corner. So now let's look at some application problem.